Okay, thanks so much for this kind introduction. Well, I am very glad to be at Strasbourg and have chance to tell you a little story about some concept that could possibly resonate in a few different communities, including your institute. When I was walking from my hotel today, Becquerel Street, here close by Langevin Street, it obviously reminded me of Curie family. And, in 2011, when we've celebrated the second Nobel Prize to Marie, Warsaw was full of different memorabilia and posters and stuff. And one poster was really good. It showed Marie with this little balloon from her mouth saying, "Men also can do science." So actually, there have been some very good links of Curie family to us, especially Eva's. So Eva, as you know, was a very different spirit from Irene and Marie as well. And she used to say this anecdote that at the table, at the dinner at the Curie house, there was Pierre, obviously a Nobel Prize winner, Marie, double prize winner, Irene, prize winner, and her husband, also Nobel Prize winner. And they would say to Eva, "You're the only one that didn't get Nobel Prize." But of course, it's just an anecdote because Peter was already dead at that time. So, so all this popped out to my head walking around here. Okay, so I'd like to tell you about a certain relatively new concept and share it and think together with you whether we could possibly find a way to apply this. As you will see, there is already one example. But this concept can be pushed much further than a single, relatively modest example of application. I come from the University of Warsaw, which is this is the main gate to the university. But this is a Center of New Technologies. It's a relatively new 2012 building where that's a concept of a research institute within the university. In other words, we do not need to teach at all. We teach only if we want to teach. And I actually wanted to teach a little, not much, and I taught sciences, but now I teach only humanities, and that's a real fun. I talk to humanities from all different faculties of the university, and there are, of course, many. University has something like 30,000 students. So all these different faculties, people come and listen about science, which of course must be put to them in a very different way than you talk to scientists. Now, people who contributed to this research are mostly here, mostly my postdocs and PhD students, and also Jose Lorenzana, an excellent physicist from Rome. And there have been some funding for this, mostly from the Polish National Science Center. So what I will show you was basically an accidental outcome of a research project, which then was turned into a new research project because we thought it's pretty general. Now, before I present the concept, I want to remind certain simple things about, first, redox reactions. The redox or electron transfer reactions are one of two most fundamental types of reactions in chemistry. You have acid-base and redox reactions, and that's how you categorize everything. And you can also build a common umbrella for the two, so you can have a more elaborate scheme. But basically, redox reactions are characterized by completeness, so that typically the equilibrium constants for these reactions are very large. And therefore, these reactions either proceed or they do not proceed. It's as simple as that. So if you mix a reducing agent and an oxidizer, if you forget kinetic obstacles, at the end of the day, everything will react to the final products and to the until one of the reagents is totally used. Many of these reactions are extremely violent. Now, this is an example of the reaction between AgF2, the compound I am very interested in, and very thermodynamically and kinetically persistent SeCl4, and you put one droplet here, that's already a lot of sparks, second droplet, third droplet, the game is over. Reaction is completed. So it's very difficult to control redox reactions. There is some control in chemistry, of course, especially through acidity and basicity, but it's really modest. And this completeness means that in most cases, you exchange integer number of electrons. So we put kids at school to write redox reactions, iron 3 getting reduced to iron 2, there is 1 electron exchange. Manganese 7 to say manganese 4, 3 electrons exchange. It's always an integer value. However, there are compounds that pretend to have non-integer oxidation states of elements. So if you take iron O, that's iron 2. If you take iron 2O3, it's iron 3. But this very, very old known Fe3O4 seems to have a peculiar oxidation state of iron of 8/3+, which is non-integer, of course. And the truth about this compound is, in fact, it has both iron 2 and 3 in a certain proportion. So if you just look at the formula, it's fooling you. It's a mixture of known oxidation states. And there is a vast number of compounds like this, and we call them mixed valence compounds, in a sense that you can look at the crystal structure and pinpoint iron 2 is here, iron 3 is here. There is no mystery. Such systems are usually isolators. So they do not conduct electricity well. However, there seem to be a much smaller number of compounds that have formally non-integer oxidation states of elements. But these oxidation states cannot be split to some integer oxidation state. For example, there is a compound Ag2F. It's not AgF2, of course, which I showed before. It's Ag2F. That's a really well-known compound. What is the oxidation state of silver there? Well, one should say half plus. But someone would say, okay, for sure, there must be silver 0 and silver plus in there. But you look at the crystal structure, and it's not so. Every silver is equivalent to another silver. And therefore, the real oxidation state is half plus. So this is a compound from the class, a relatively narrow class, known as intermediate valence compounds. Not the mixed valence, but the intermediate valence. And such compounds, on contrast to the previous group, are usually metallic, so they conduct electricity very well. Why? because you have, in the solid state, you have electronic structure and you've got bands. And if there is some non-integer oxidation state, it means there is some peculiar electronic structure, like in this case, D10 S 0.5. And this means, in the first approximation, that the S band is just half filled. And this means a metal. So this is a nice example of intermediate valence compound. So is iron 3s. You probably never heard about this compound because it does not exist on planet Earth at normal PT conditions. But it exists at high PT conditions, and it is immensely important compound. Because all theories about how the nucleus of Earth looks like, and that's made of iron and nickel, of very heavy elements, have recently been shaken by those discoveries that some sulfur, a light element, can actually dissolve into the core and can form compounds like this. So there is some cycling of sulfur even in the deep core of planet Earth. And this, again, is a peculiar compound which has just one type of iron in its structure. And it's not iron 1 plus or 0, that's intermediate valence. There are also compounds which by their nature are non-stoichiometric, like titanium oxides, where X is close to 1 and O is close to 1, but they can vary broadly between 0.9 and 1.1, for example. And this also implies that there must be intermediate valence. And usually there must be metallicity. Now, this compound is really interesting because you can say, okay, what is the difference between compound TiO and the compound Ti 0.9, O 0.9? Well, the difference is, in the latter, there are defects and both titanium sites and oxygen sites, but the reduced formula is just the same. It's 1-to-1 compound. So these two compounds have identical formula, but they have different densities and very, very different properties. That's why it's so important not to know just stoichiometry, but to know the true nature of your species. And then finally, people have learned how to generate non-stoichiometric compounds using what's called doping, chemical doping. So that, for example, you can start with lanthanum-2 copper 04, and that's a black insulator. But if you substitute some lanthanum for barium, which is of course not isovalent, then you generate copper 3+, aside from predominant copper 2+. And that compound is not just metallic. If you chill it to sufficiently low temperature, you'll get a superconductor. A famous one, really. The Nobel Prize worth. If you think that at 3-element composition, lanthanum, copper, oxygen, with a slight substitution for barium, got these people Nobel Prize, you'll think, gosh, how little we know about compositions of 3 elements only. The phase diagrams, the properties. Now, if you go to high pressures or high temperature region, you will learn that we know very little about elements, not just chemical compounds. There is a lot to discover. And the compounds like this one, there are much more. So for example, if you dope silicon with phosphorus, in fact, that's a non-stoichiometric compound. And you generate a very heavily doped semiconductor, even similar to a metal, if you do so. And should I convince you that it's important? We live in the era of semiconductors, of computers, of solar cells, of transistors, of central processing units, and everything, you name it. This, if we didn't learn how to create non-stoichiometric compounds in a repeatable manner, precise manner, this would be, we wouldn't be there where we are. What is this? This is boron-doped diamond. Diamond is, of course, colorless, but boron-doped diamond is black and it's metallic. You can make electrodes from it, and you can do electrolysis on these electrodes, which you cannot do on diamond, of course. And the beauty is, this is equally chemically resistant as diamond. So you can do crazy electrolysis in some really extreme conditions, extreme solvents. Why? Because we know how to fool nature and dope and create non-stoichiometry. So if you think about it, in fact, this all defies law of definite proportions, which is the cornerstone of chemistry. We would never learn about atoms if people didn't discover that most of chemical molecules combine themselves into some integer proportions. If people knew how to do these compounds well before Avogadro, we would probably have a big problem. Of course, science proceeded in a totally different way. It was simple. They first learned there is 2 hydrogens per 1 oxygen in water, and there cannot be 2.1 hydrogens. But these compounds defy the law of definite proportions. There are tungsten broses. There are systems which can store lithium in the lithium batteries. There are the new generations contain of organic polymers, but they all share the same feature, non-stoichiometry and metallicity. There is this guy which I mentioned, superconductors. There is giant magnetoresistance, the beautiful systems, manganite. There are non-stoichiometric high TC superconductors at very high pressure, which have crazy formula. If you asked a student to draw the formula of lanthanum hydride 10 years ago, and he would put you this, you would not pass him at the exam. Now, you can use a trivial fluoride, calcium F2, but if you dope it with yttrium, you suddenly get a tiny excess of fluoride anions in the structure, which are extremely mobile because they do not fit to fluoride structure. So suddenly you generated excellent fluoride ion conductor, which is ionic conductor, not electronic conductor. So from solely these examples, including famous conducting polymers, which were prepared by accident, because a student used 1,000 times higher concentration of iodine than he should. And he generated doped polyacetylene, which proved to be not insulating, but metallic, golden, shiny, and conducting current as well as copper metal. And polyacetylene conducts electricity as well as wood. So that's a revolution of property. So solely from these examples, you can see how many amazing properties come with non-stoichiometry, non-integer oxidation states. And no doubt, many Nobel Prizes were awarded for these discoveries and also building devices based on such compounds, right? Different transistors, light-emitting diodes, and so on. It's all about non-stoichiometry. So the last piece of introduction is about a certain feature of a redox reactions. That is a harponing effect. Now, if you take cesium and fluorine atoms in a vacuum, and you ask a student what will happen, will they react or not? The good student will tell you, of course, they will react. But then you say, okay, but place these atoms a kilometer away. Will they react? Then the student will have a problem. Because he knows cesium is immensely reactive, an atom is even more reactive than a solid. then fluorine atom is more reactive even than a molecule of fluorine. So they should react, but they are 1 kilometer away. And then a very good student will realize that ionization potential of cesium, so expelling electron to vacuum, is in fact larger than electron affinity of fluorine. But because they are far away, you must expel electron to vacuum and only after some time put it on fluorine. So there is a price to pay at the beginning, and this is not compensated by electron affinity. So this will not happen. When will this happen? Only when the atoms come at sufficiently close distance, because then what will additionally help the reaction energy-wise is Coulombic effect of attraction of ions once the electron is transferred. And that's a trivial exercise to calculate what is that distance, because you know electron affinity of fluorine, ionization potential of cesium, and at what distance R Coulombic effect will suffice to transfer the electron. The response is amazing. 3 nanometers sharp. So if atoms are more than 3 nanometers away, nothing will happen. But if they are closer than 3, there will be sudden electron jump, so-called harpooning effect, which is really well known for 100 years. It's just not put into the textbooks for some reason. So the message from this is redox reactions, in fact, have a distance dependence, which is normally forgotten. And that distance dependence is relatively trivial, so that either at large separation, there is no reaction, although this can be immensely reactive thing. But at a certain separation and below, there is the reaction. So it's a 0-1 effect. Okay, now I pass to the core with that introduction to the what I call chemical capacity. Now you see, we can think it's a Gedanken experiment. What will happen if we have an oxidizer and reducing agent placed as monolayers, placed at a certain distance? Because we know cesium and fluorine showed this interesting behavior, but now we don't have atoms. Now we have layers. Now we have solid state. They are separated by some spacer. They can be placed on a substrate. There can be a cap so that everything stays in place, a protective cap. But the core of the thing is oxidizer, reducing agent, and a spacer. Now, the difference to cesium and fluorine is that these are solids. For example, MgO layer, AgF2 layer, some separator here. And if these are solids, they do not have discrete orbitals, but they have bands. And bands, unlike orbitals, can be partially filled. So now the basic exercise is to put things into calculation. That's your oxidizer. This is the reducing agent, not a very strong one, I must admit. And see what happens if you place them with this separator, with 2 layers of that separator here. Well, what will happen is you will have for 2 layers of a separator the transfer of about 0.15 electrons between these layers. But if you decide to use 1 layer of a separator, it will be over 0.2 electrons already transferred. But if you use 3, it will be slightly below 0.1 and so on. So this curve is a bit like hyperbola. So this graph is very simple, but it has many sides to it. One thing is we can control charge transfer between oxidizer and reducing agent in a manner that does not lead to integer number of electrons exchanged. That's something new. But one will say, okay, but you just showed us the cases where, for example, you take cobalt-02, you dope with lithium, and you also do this. This is definitely true, but what's the difference? Here, I didn't change stoichiometry of these layers of oxidizer and reducing agent at all. I didn't permit any contact. When lithium enters COO2, it enters the structure, travels through the structure, sets there, and this is how it dopes. I didn't do that here. My layer here is here, that one is here. They do not move. And yet they dope each other. They dope mutually each other. So one dopes the other and the other dopes this one. So one is doped with electrons and another is doped with the same number of holes. And by controlling the separation by the numbers of separator layers, I control charge transfer. And now I can use a stronger reducing agent, and for the same separation, I will have stronger charge transfer than for a weaker reducing agent. And it should be so, of course. But it still will not be integer value. So I have a new tool to control charge transfer, and in this way to control properties of these layers, of one and the other. Because they have partially filled bands, and they will both be metallic now. And they were insulating before they met at some distance. So think about this as a sort of experiment when you have two insulators, thin layers, and you bring them closer and closer, and you do just nothing, and they become metallic. It is not chemical doping, right? I didn't alter stoichiometry whatsoever. And yet, they dope each other. Looks like a miracle, but I assure you it's not. Okay, so you can in fact write this equation of the reaction here, and this will not be the equation that kids put at school, iron 3, iron 2, because there is this delta here, which is non-integer. That's why there are no such equations in chemistry textbook. Okay, now I want to tell you, before I pass to the organic polymer thing, that this concept, when we wrote the paper in 2021, we were desperately looking whether that's new, of course. This is what scientists do. We want to be sure that no one had this idea before, and we want to be fair to everyone who even touched the topic. And when the paper was already in proof, we found one very interesting paper, experimental one in nanoscale, 2015, where they have done many different experiments on graphene in the paper, and we could find in that paper a single experiment which wasn't at all important. They weren't, let's say, even using this wording that we use, when they doped holes, a small amount of holes into graphene solely by using oxygen as a hole carrier without any contact with graphene, because everything was separated by silica. They also had needed some support to immobilize oxygen. So at some point, silica always forms very, very thick chunks when you deposit it from vacuum. So their separator was immensely thick, about 30 nanometers. And in another experiment, about 50 nanometers. So it's far, far away from our system, where the separator is basically about 1 nanometer. So in their case, and as you know, this effect really decreases substantially with thickness. It must, because if you separate layers to infinity, the same thing as cesium and fluorine, nothing will happen. Electrostatics is not paying back. So they saw small effect of whole doping to graphene, but sufficient to be seen. Why so small? Because of a huge thickness of silica. In our case, the effects are 3 orders of magnitude higher in our theoretical experiment. So you realize this, and we added this, of course, to the paper and said, look, we think one precedent is already known, but basically there is a huge room for improvement, 3 orders of magnitude. And before I pass to organic polymers, I want to place, and why do we call this chemical capacitor? Well, because of this dependency. What happens if you take 2 metal plates and you apply external voltage, you store a charge. The more voltage you apply, the more charge you store, and this charge is non-integer in any way, right? So if I put here voltage instead of separation thickness, I would have very similar curve. So this device resembles capacitor, except there is no external voltage. What is therefore doing our job? Well, it is the difference of chemical potentials, not electric potentials. So if you take electrochemical cell, you have a difference of electric potentials, which can be used as a difference of electric potential. And your separator between electrodes is really macroscopic or microscopic at best. You can use this to get energy. If you now rip all the inside and you leave 2 electrodes, you will be left with a standard physical capacitor. Now, you must apply difference of electric potentials to get charge separation. But if you now use your electrochemical cell, whatever battery you have, and you rip out all electrodes, you are left with this. What is it? It's a totally spoiled battery. It will not work unless this separation is in the nanoscale. Then you have chemical capacitor. And now the difference of chemical potentials can be changed to charge separation, depending on the distance. This device is good not for energy storage. It does not generate any electric voltage. It does not permit you to recover the charge stored. It's good for nothing except one thing. What you do in this device, you can metallize these layers by proximity. So now, imagine one layer is, say, sodium chloride. You and I know what properties sodium chloride has, but have you ever thought what properties does sodium chloride 0.9 plus have when it's metallic? What can it do? What material properties can such a layer have, except it will be for sure metallic? Or 1.1 minus, or whatever. So, in fact, in the triad of chemical potential, electric potential, and charge, this is a new member of a triad, right? You have the triangle of properties. And there is a nice equation that my collaborator, physicist Jose, came up with, which really nicely describes the behavior and the charge separation, depending on the chemical properties and capacitances and so on. Okay, so another way to view it is, I call it explosions on the leash. Try to bring a reducing agent and oxidizer together and touch them. There will be an explosion. But if you just approach them, and there is a separator, they will not explode. They will just transfer some non-integer charge. Okay, so as I said, this could be good for metallization. The trick is, you know, the valence band of one substance and the conduction band of another substance should overlap, and they will mutually dope each other. Do you know what effort there is to metallize this AgF2 with a gap of 3.6 electron volts? You can use 1 terapascal. It will not metallize. The same with magnesium oxide, even broader band gap. High pressure people, ultra high pressure people do such experiments, typically in the range of few hundreds gigapascals, sometimes a terapascal. You cannot metallize magnesium oxide. The band gap is too large. But use the trick of overlapping its valence band with the conduction band of an oxidizer at a distance. You will get metallization. Now, my obsession was metallization of AgF2. That's why we used this, you know, layered setup to metallize AgF2 in this paper. But maybe I skip that. But I want to propose the following to your community. As the example of graphene showed, as the example of AgF2 and MgO showed, you can really be using different things. That's a very general concept. In our theoretical experiment in angewandte paper, we needed, for technical reasons, to have perfect epitaxy, because you cannot calculate things if you don't have epitaxy. But experiment in nanoscale 2015 doesn't have any epitaxy. There is iridium metal, oxygen molecules on it, which do not form any crystal. They just wander on the surface. There is silica, chunks of silica, separator, which have totally different lattice constants. And suddenly graphene put on the top, which does not match any of the three lattice constants. So epitaxy is not needed for this. You can be playing a lot. And now the idea is, could one construct a prototype of this chemical capacitor using some organic molecules or organic polymers? Let me emphasize again that the idea is not to take undoped organic polymer. In fact, my master has been done on organic polymers, so I have some affinity to this, conducting polymers. But the idea is not that you take undoped system and you dope it chemically or electrochemically. This is trivial. Everyone knows this since the 80s. But the idea is that you take two non-conducting parent compounds, stoichiometric ones, and you put them separated by some inert separator, for example, polyethylene, and they metallize each other by proximity. So, in order to do this, you must have organic molecules that will fulfill this condition, that the valence band of one of them, reducing agent, will overlap with conduction band of the other guy, oxidizer. Therefore, it's best if you use strong organic oxidizers and strong organic reducing agents. And of course, there are systems like this, TTF, chloranil, everything that is known, they form so-called charge transfer organic salts, right? These are beautiful experiments also from the late 80s, and this is a huge field. But in these salts, they either form segregated stack, they are very close to each other, no separator, or they form alternating stack, so they really touch each other. The experiment I propose is, and I emphasize, very different. Place a layer of strong organic oxidizer on some substrate. Place a separator, and then place a layer of organic reducing agent, and monitor optical and electric properties, because they will change dramatically. From insulators, you will get metals, shiny, reflection, everything will be changed. So you could use polyacetylene, you could use TCNQ, maybe tetrafluoro TCNQ. One difference, one aspect here is that if instead of using polymers with a band structure, you use molecules, you will have charge transfer, of course, but you will not have metallicity due to polaron formation. But this is another story. So, also before I really close, I was thinking there are some zeolites, beautiful zeolites, which have hexagonal pores, one close to each other, which have a diameter of 3 nanometers. And the wall thickness between the pores is about 2 nanometers. So that's a right scale. If we were able to fill such pores with strong, for example, organic oxidizer reducing agent close to each other, they would form this in a bit different setup, not really layers, but something similar. Unfortunately, the nanopipettes, the best nanopipettes we can have today have the diameter of 10 nanometers. And here we must have about 1 nanometer. So we are 1 order of magnitude too short to make this idea work in this setup. But maybe you have other ideas. So what I try to show you is that we can do non-integer redox reactions in a controllable manner. And the governing factor is the distance between reactants. And we can use this charge, depending on the distance, as a new variable in property control, because chemists use chemical potential, pressure, temperature, that's it. Now you could use additionally charge as a property controller. Sodium chloride 0, sodium chloride 0.1 plus 0.2 plus whatever. Properties will change. So it's a new possibility to play chemistry. True, this possibility is not for every chemist. It's only for nano people. That's true. But still is better than nothing, right? And we could possibly study this novel device, chemical capacitor, and discover its functionalities, because you can think of many. I can think of many immediately, how you can use this. Now, for physics, it's important because you are doping through proximity and you are metallizing the layers, and you may even generate superconductors in this way without the need of an external pressure. So, there is something for everyone, but you must be a nanoscientist. Now, I am not. So for me, unfortunately, this is just a dream. That's why I'm sharing it with different people. I already have with many, and looking ways to maybe materialize this in some new setup. Okay, so with that, I thank you for your kind attention.